Okay, welcome to another episode of the New York City Category Theory Seminar, and we have returning, I don't know, third, fourth time, very nice, thank you, Larry Morse from University of Illinois at Binghamton. I think
no, somebody else. No, this is Indiana University.
Indiana University, Bloomington. Sorry. I was there. It's a beautiful place.
Yeah, you were here.
Right. Okay. On Kripke, Vietoris, and Hausdorff Polynomial Functors. Okay. Take it away, Larry.
Okay, it's nice to be a repeat customer, a repeat offender, a repeat participant here. And so here's what's going on with this. So this is a very bird's eye view of the whole subject that I'm dealing with here. So on the left, we have various kind of algebraic concepts. And on the right, there's something of the coalgebraic or the dual in some sense flavor. And there's a whole systematic set of the concepts and stuff like that. And what I'm doing today is really just looking at initial algebras and final coalgebras in a very the construction of how they work in the most usable way and a variation of that. So this is why I do the subject is because I'm interested in this general chart. And what I'm doing is a set of mathematical results that's really related to the second line. Okay. So yeah, you should definitely stop me. I want this to be accessible to a category theory audience. So if we have a category and an endofunctor, so that means a functor from the category to itself, then an algebra for the functor is just a morphism of the form going from FA to A. So it's an arrow, morphism from FA to A. And if you have two of these, let's say little a going FA to A and little b going FB to B, so therefore you have the top part of the square and the bottom side of the square. So the top is an algebra, the bottom is an algebra, and what's called an algebra morphism or an algebra homomorphism is just a morphism in the base category A, such that the diagram commutes, and where you need category theory is in order to apply the functor, to this morphism F, in order to even talk about the commutativity of the square.
One question. So far, it's just a functor. Doesn't necessarily be part of a monoid or anything like that.
Yeah, it won't be. It won't be like algebras in it won't be an Eilenberg Moore algebra in general, and it won't be the coalgebras here are not like the coalgebras in Hopf algebras or something like that. It's actually simply a functor, so it's actually much more general. So that means the results here are not going to be. They may not be interesting to you if you're, I remember talking to one of my colleagues in Indiana who said, "What is this coalgebra that you do?" And I put, basically I put the coalgebra square up here, which is coming up. And he said, "What? There's no extra structure, like a vector space or a monoid or stuff like that." And I said, "No." And then so he was, okay, nice to talk to you. So he was, out of my office. So it was kind of like wasn't interested because the other structure that people want are missing from here. But there's a compensation, which is that it's much more applicable this way. So so that's an algebra, and an initial algebra is an initial object in the category of algebras.
Mm-hmm.
So was somebody else asking something?
Oh no, sorry.
Okay, so of course the morphisms of algebra constitute a category, and thus we can talk about an initial object. An initial algebra is an initial object in the algebra category, which means it's an algebra like on the top side of the square, such that for every algebra B, like on the bottom, there's going to be a unique algebra morphism, which I called phi here, making the square commute. So the most vanilla example is on the category of sets, and the functor is 1 plus x. So an algebra is therefore going to be just any set x together with a map from 1 plus any set, let's call it A, together with a map from 1 plus A into A, and a map of that form. Well, the part from 1, that's a one element set, just picks out an element of capital A, and the other half of the morphism, picks out an endofunction that is a map from A to A. So basically, the data here, 1 plus A to A, is just basically a repackaging of an element of A together with an endofunction from A to A. So the most natural example is going to be the natural numbers. So where I take natural numbers, where I'm going to take 0 to be the picked out element, and successor to be the successor to be the endomap. And then initiality is just saying that for every such kind of data, like on the bottom of this square, there's a unique map that makes the diagram commute. And this is called the initiality. So that means that's what it means for n together with this map 0 and s to be an initial algebra for the functor. And that's just tantamount to the recursion principle from natural numbers. So that's like the most important definition principle for the natural numbers is recursion, right? Which would say that if you give me any set, capital A, and any element in any endofunction, just the stuff we've seen, there's a unique map phi from n into a that is defined by recursion in the usual sense.
Should the name Lavier be mentioned here?
You could mention Lavier if you want. I think Lavier actually.
Well, I think he defined this as an axiom.
You could take this to be an axiom. That's right. In fact, you could take the. I think Lavier might have been the first person to recognize that recursion on n is tantamount to initiality. I mean, I know
that was my point.
Yeah, he may well have been the person to do it. And so he noticed that recursion is a on n, the usual one is tantamount to initiality of the algebra. Okay, so here's another one. So if you vary the functor from it was 1 plus x a minute ago, now 1 plus x times x, then what you get here is actually the algebra of finite trees. So I won't go through this in such detail, but basically what you get is the initial algebra is the set of finite binary trees. So finite trees that every point is either a leaf or it has two children. And there's a recursion principle, and you need to work out what the structure is, and you need to check out that the recursion principle for trees, for finite trees, is exactly the same thing as the initiality principle here. But it is. And in fact, the slogan going back here is that, well, recursion is generally speaking a map out of an initial algebra, like it's a map out of the natural numbers. Now, there's going to be a dual concept that we'll see called co-recursion, but in general, recursion in math is often is a map out of an initial algebra. So it works in trees, various other things like that. Okay, so here's some more definitions. So an algebra, remember, is a map from FA to A, and turning the sense of the arrow around gives you a co-algebra. So the name co is just because it's turned around. So a co-algebra is a map from A to FA, where A is just some functor. And of course, in order to talk about co-algebras, you have to have a category and you have to have a functor from the category to itself. So on set, so here's an example. On set, we have a functor 2 times x to the a. So that takes a set x, and a is a fixed alphabet. So this is about automata. So a is a fixed, you think about it as the input letters to an automaton. And so now this gives you a functor. It takes a set x to 2 times x to the a. And then you could ask the question, well, so what's, let me go over to, so what is going to be a coalgebra? So a coalgebra is going to be a morphism of exactly this form. So I want to think about, I called it automata here, which you should think about the S as a set of states of a deterministic automaton. So what is a deterministic automaton? Well, it's a set of states, and each state is either tagged as accepting or not. And so that's the map from S into 2. It's either going to say, hey, it's accepting or not. And then it's a deterministic one, so that for every alphabet symbol, it gives you a map for every alphabet symbol and for every state, it gives you a successor state. And when you repackage that a little bit, you see that an automaton is a coalgebra of this functor. So again, here's again algebras and coalgebras. So algebra, so this one here is an algebra on top and an algebra on the bottom. And what it means to be a morphism is the little f on the side. On the coalgebra side, it's exactly the same. So the top is a coalgebra, the bottom is a coalgebra, and what it means to be a morphism is a map, like, okay, so it's a morphism from A to B such that this diagram commutes. And again, we get the morphism on the side by applying the functor to the morphism on the left. And then there's the definition of an initial algebra. So an initial algebra is an algebra that you can go to every algebra in a unique way. And a final coalgebra, which is the main topic of this talk, is a coalgebra so that you could get from every coalgebra to it uniquely. So it's exactly the dual kind of concept. So here's a kind of chart of why somebody would want to do this kind of stuff. I mean, for this talk, the main reason somebody might want to do it is that you recover a lot of interesting objects in mathematics by asking for initial algebras and final coalgebras. So we've seen that for the functor 1 plus x on set, the initial algebra is the natural numbers together with 0 and successor. If you change the functor to this one, you get finite binary trees. If you change it to this functor, 1 plus a times x, where a is a fixed set, you get finite sequences from a, and you get the recursion principle for how you define functions by recursion on sequences. Now you can vary the category too. So if let's say you vary the functor from set to metric spaces. So that's what I'm going to do in this talk is to do something on set and then to look at it in other categories. Well, we have the same functor, 1 plus x squared, but I want to change the category. And what it would be the set of finite binary trees with a certain metric. So maybe I'll tell you what that metric is later. But if you had to put a metric, a distance function on the finite binary trees, I think there's only one or two natural ones, and it would, it's not going to be the discrete one, right? It's going to be an important one. So you're going to probably get the right one. If you move from the category of metric spaces to the category of complete metric spaces, then in fact you recover both the finite binary trees and the infinite binary trees. So you by changing the functor and changing the category, you get a lot of interesting stuff. So now in terms of the final coalgebras, well, if you take the same functor 1 plus x that we saw a few minutes ago, and you ask for the final coalgebra of it, it turns out to be the natural numbers with an extra infinity. And if you ask, what about this 1 plus x squared? It turns out this would, in fact, be the set of finite and infinite binary trees. Actually, it's the same as this one, except on set, it doesn't come with a metric. It just comes as a set. And if you go to this one, 1 plus a times x on set, you would get the set of finite and infinite sequences from the set A.
I'm just wondering, with the first example, just like with the example the other direction, you gave a simple way of seeing why that would be the natural. Is a simple way to see why if you reverse the arrow, you get natural numbers with infinity?
No, no, you have to work it out. No, I mean, there's a whole load of theorems that I'll point to that kind of do this, but I wouldn't say that there's an easy and immediate way to do that. No, I mean, actually, no, I don't think that, like I asked my students to guess it and they guess, the ordinal numbers or something like that. No, there's not really an easy way to do it. But I think in the course of this talk, I will actually give you enough information that you'll be able to do it.
Well, thank you. I don't feel stupid this way.
You definitely are not. No, don't feel stupid. I'm just telling you, I'm kind of giving you a quickie summary of a whole lot of stuff, which is kind of what I'm going to be doing in this talk in general.
Well, one second. What
I just to follow up on that, when you say natural numbers plus infinity, mean all the natural numbers and the quote number of called infinity, right?
Yeah, you can call it whatever you want. I mean, it's natural to think about infinity, but then you have to think about, well, as a coalgebra, you have to think of mapping that set, right? The natural numbers with another one into one that set. And you have to check what does the final coalgebra mean? What does it actually mean that it's the final coalgebra? And it's like a few lines of calculation, but it has to be done. Yeah.
Mm-hmm.
I guess not to disrupt too much, but I would say that once you get a handle on working with this stuff, I feel like that things like that, you get a pretty good intuition pretty quick why things like that happen. And once you get the sense of final coalgebras, then something like that is easy because you sort of understand, we can talk about it later, but yeah.
That's actually right. In fact, so that's all that kind of stuff is generally what this talk is about. So thank you for jumping in on that. Yeah, okay, so let me show you formal languages as a final coalgebra. So this is this also would be kind of interesting, and I don't think it would be exactly obvious, but so let's think again the functor on the category of sets, which takes a set S to 2 times S to the A. where A is some alphabet, like in automata theory. And now a coalgebra is a deterministic automaton, the way we've seen it. But here's another interesting coalgebra. I'm going to take L to be the set of formal languages on my alphabet. So what is a formal language? A formal language is a subset of A star. So that means, right, it's a subset of the set of finite words. So that means this L here, this fancy L is the power set of A star. And now I have to tell you how I'm going to make this into a coalgebra. So that means I need to map little l that takes the formal languages to 2 times L to the A. So I'm going to take a formal language, and I have to give out either a yes or a no, right? As something in 2, either yes or a no. So I'm going to say yes if it contains the empty word, and no if it doesn't contain the empty word. So again, I'm applying this to a formal language. And then I'm going to, now what about this part here into the set of functions from A into L? Well, this is what are sometimes called Zhezhovsky derivatives. So what is that? So that means it takes a formal language L. Let's see if I can actually write here. I can't really write, and it kind of is disruptive when I do that. It takes a formal language and an alphabet symbol to the set of words, so that if you stuck the alphabet symbol on the left, you would get into the language that you started with. So it's a natural map in automata theory. And so that's an example. I'm going to claim that that's the final coalgebra. And what does that mean? That means if somebody gives you an automaton, I need to have a unique map from the states of the automaton into the formal languages. And actually what the map does is it takes a state in the set capital S, and it gives you the set of words which would be accepted if you started the automaton in that state. So it's actually the language acceptance map of an automaton. So that's kind of like what all this stuff is about. It's like final coalgebras are like the set of languages in general, the set of things that you could map into in a canonical kind of way. And going back to my thing here, so an algebra is like a set with algebraic operations, and a coalgebra is like a set with transitions and observations. So the most final one, is going to be like what you could observe with an automaton. And if you had an automaton, what the kind of things that you want to observe are the languages of words that you would accept at all the different states. So this is on an intuitive level, but this is kind of substantiated by this example of the final coalgebra of this functor on the category of sets. Okay, so what this talk is really about, coming up with final coalgebras in complicated situations. And one thing that I want to use right away is a lemma due to Lambeck that's, I think everybody in category theory probably knows, that if you have an initial algebra for a functor, so if you have any initial algebra, then the structure map, that is this is what I drew with a capital A before. So the structure map of an initial algebra is a categorical isomorphism. That means it's invertible. And this holds for initial algebras, and by duality, it holds for final coalgebras. And I can give you these. This is well known, but I can. The proof is in these slides, and if you wanted to see it, you could look at these later. I could send it to you or put it up or something. So the point of this is that this gives you a negative result about initial algebras on set. So I'm going to look at the power set functor on set. So the power set functor on set takes any set into its power set, that is the set of all subsets of it. And any function from a set, let's say a function between A and B, we have to map. So I now have to tell you how to map the power set of A to the power set of B, given that function from A to B. And what you do is you take a subset of A to its direct image under the function. And so that's a way to get a functor on sets called power set. And so there's a famous theorem of Cantor. It's actually the very first theorem in set theory, is that there's no function from any set onto its power set. So Cantor's diagonal method, the first theorem I think in this kind of stuff in the set theoretic vein, is exactly that. There's no function from any set onto its power set. And that means that there's no bijection of any set with its power set, because every bijection in set is one-to-one and onto. So that means, and with Lambek's lemma, is that this functor power set has no initial algebra and it has no final coalgebra. So let me make sure everybody gets this. On power set on set has no fixed points because no set is isomorphic to its power set. In fact, no set can be mapped onto its power set by Cantor's theorem, and by because Lambek showed us that any initial algebra, the structure of it is an isomorphism categorically. That means in set, that means that it's a bijection. So that means that this functor can't have any initial algebra and it can't have any final coalgebra. So that's a negative result. And that's part of what this talk is about too. Now, to get around this, like supposing you really like final coalgebras, by the way, some of us do. So you can sort of like move the goalpost by changing set to a category of classes, which I don't want to talk about. But I do want to talk about the next move that you do is that you could take a cardinal, let's say kappa, which could be a finite cardinal or an infinite cardinal, and then you change the power set functor. So instead of giving you all subsets, you say, I'm going to take only the subsets of size less than kappa. So that's a functor also with the same action on morphisms. So that cuts the functor p down to p sub kappa. And then it turns out that, well, in fact, if you take the cardinal kappa to be omega, that is the Aleph 0, the first infinite cardinal, you would get the finite power set functor. So that's going to be one of the main things I talk about today, the finite power set functor. So it takes every set to the set of its finite subsets. And well, if you know some set theory, the set H kappa, the sets of hereditary cardinality less than kappa, that would actually be the initial algebra of P kappa. And the final algebra is harder to describe, but I'll get to it later today.
So Cantor's theorem fails for P kappa, for P finite?
Yeah, of course it does. Yes, Cantor's theorem is completely wrong. I mean, for
Well,
example,
Cantor's theorem tells you that the thing can't lie in kappa, has to be a bigger thing. That's all.
But I mean, there is everybody. But for omega, let's say Cantor's theorem is completely wrong for omega because there is a map from omega onto the set of finite subsets of omega, and that's the end of the story. So Cantor's theorem is false for the finite power set. In fact, it's false for every infinite set has the same size as the set of its finite subsets.
Okay.
So Cantor's theorem is completely wrong for that. Yeah. So what I'm interested in here is, I would like to show you an existence theorem for final coalgebras. And let's see what happened to this thing. Yeah, I want to show you what I'm going to call a go-to method. So this is a little bit out of order. So there's a kind of thing that I'm going to call the go-to method for final coalgebras, which is like, how do you usually get your hands on them? And I want to show you when it works and when it doesn't work. And in the case when it doesn't work, the main contribution of our paper is a kind of modification of the method that does work. So that's what's going on here. And also, I want to show you some non-existence results for final coalgebras or initial algebras also that are like Cantor's theorem. So since we talked about that, I'm glad that people asked about this. So for example, here's Gleason and Dilworth's theorem. So if you look at the category of posets, so here's the category of posets, and one natural power set-like thing is to take a poset and look at all down-closed subsets. So all subsets that are closed downward in the order. And now that's a poset. When you order it by inclusion, that's a natural poset. And now I want this now to be a functor. So I have to say, what do you do for a monotone function between posets? So remember, the category of posets, the morphisms are the order preserving or the monotone functions. And so I have to tell you how df works. And df of a downclosed set is going to be the set of things that are less than an image. So this is a natural way to define this as a functor. And in 62, Gleason and Dilworth showed Cantor's theorem for posets, which is that for any poset, there's actually no monomorphism from dp to p. So it's again, so remember, Cantor's theorem is that there's no epimorphism, there's no map surjecting onto it. So I actually modified Gleason and Dilworth's theorem to actually prove Cantor's theorem for the category of posets. So for any poset, there's actually no onto function, no order preserving onto function from the downsets of P back to P. So that means that as a result, this D doesn't have an initial algebra and it doesn't have a final coalgebra. So I'm interested in all the possible results that are kind of like this in this talk. So I'm going to tell you the go-to kind of methods for this. So here's how you get an initial algebra usually, or in the good case. Here's how it goes. So supposing you have a category and a functor on it. So the category is this A, and the functor is F, and supposing it has an initial object. So initial object means you can map into anything uniquely. So you could apply the functor to the initial object. That's F0. And of course, by initiality of 0, there's a unique map, this bang here like this. So this is 0, and here's F of 0, and there's a unique morphism like that. Now, if I take F and I apply it to this part of the picture, I get the one going F0 to F double of 0, F0, and F bang on the top. And then I keep applying this like this, throughout the natural numbers. And I take the limit, sorry, the co-limit. So the co-limit is the categorical co-limit. And the categorical co-limit, for very general reasons, there's going to be a map from the limit L to F of L, which you would get by banging F on the same sequence here, and checking out that there's going to have to be a map like this. If F preserves the co-limit, that means F of the co-limit is the co-limit of everything you get by applying F. In that case, this M would actually have an inverse. And L, together with M inverse, so M inverse is going from F, L to L, actually would be the initial algebra. So this was shown by Adamek, one of the co-authors of my paper here. And let me show you how he got that. So what Adamek did was he looked at Kleini's theorem. So Kleini was, so one time I had to speak here, I had to tell you who my academic supervisor was. So Kleini was my academic grandfather. And this is Kleini.
Remind us, who is your thesis advisor?
Yanis Moskovakis.
All right.
So this is Kleini's theorem. It was the following one. So Kleini's theorem was not about general categories. It was about a poset. So supposing you have a poset and a monotone function, that means it's an order preserving function. And supposing it has a least element 0, so at least it's less than F of 0, and that means you start iterating the function and it's going up, possibly with equal, but it's going up, 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 up. And suppose that the poset is so good that it has a least upper bound to this. So if it has a least upper bound, then for very general reasons, FL is going to be less than FL. So you check that yourself. And if F is continuous, that means if it preserves least upper bounds of chains, like this one, then L is actually the least fixed point. So Kleini's theorem is, how do you get your hands on the least fixed point of a monotone function on a poset that has least upper bounds? And so what Adamek did was he took this theorem here and he categorified it. So he took all of the order theoretic concepts in that Kleini needed, and he looked at Kleini's theorem and he categorified them. So a preorder is the poor person's category, right? A category means that you have different flavors of morphisms between the objects, and in a preorder in a poset you have at most one. And this x less than y less than x is the same thing as being isomorphic in category theory. An initial object is like a least element, and a functor generalizes a monotone function. Now a prefixed point, so a fixed point, it means it's equal. A prefixed point is fx less than or equal to x, and a prefixed point is exactly what I'm calling an algebra. And a chain is like a functor from this category into here. Continuity is like preserving colimits, and the least fixed point is like an initial algebra. So if you took Kleini's proof and simply expanded it, there's some work to be done, but this is the inspiration, is by categorifying Kleini's theorem. Now, here's an example. So let's think about the finite power set. So the finite power set is the main one for this talk. And let's take that and think about how that works on the category of sets. So I want to go back here on the category of sets. What is the zero? The zero is the initial object. That's the empty set, because you can map the empty set into any set uniquely. So this is the empty set. And now I'm going to iterate this by, I'm going to actually tell you what is this F0 if F is the finite power set. So 0 is the empty set. The finite power set of the empty set is the set containing the empty set. F squared of 0 is the set with 2 elements, namely the 2 subsets of the singleton of the empty set. And in general, they get exponentially bigger, but they're all finite sets. And you can take the co-limit, which in this case is the union. In this case, the co-limit of that sequence is the union. And when you do that, V omega, that's called V omega in set theory. And that's a fixed point of the finite power set. So every finite subset of V omega is actually an element of V omega. And that means that the identity is actually a algebra. The identity, they're the same set. So there is an identity. And by Adamek's theorem, that's an initial algebra. So that's great for how you get your hands on an initial algebra. But I want to talk about the final coalgebras too. So stop me if this is all rolling on too fast here. Okay, so so here's the idea is that we applied Adamek's theorem because the functor preserved the co-limit. So that's basically, that means that this V omega is a fixed point of the functor. If I try to roll this argument with power set, it's not really true. And in fact, it can't be true since the power set doesn't have any initial algebras. So Adamek's theorem is the one on the top here. And what Barr did about almost 20 years after him was to turn all the arrows around. And instead of starting with the 0, with the initial object, he started with the final object. So the final object in a category is an object that you can map everything into uniquely. In the category of sets, final object is any one-point set, because every set maps uniquely into a one-point set. And so Barr said, supposing that the category has a 1 and you start iterating this to get this chain backwards. So this is all the arrows are going backwards. And supposing that this has a limit. So up here it was a co-limit, and down here it's a limit. So I assume that this is the category theory audience that you know about limits. And in fact, I'll remind you how limits are constructed in the category of sets. So in this case, there's going to be a morphism from FL to L. In the good case, the functor preserves the limit. That means if you apply the functor to the limit diagram, you get the same thing as if you would get if you applied it individually to each point. In that case, this morphism M is invertible. And when you invert it, you get a final coalgebra. So in fact, Barr, I think wrote this and proved it, but in fact, Barr didn't exactly have to prove it because his result follows from Adamek's theorem by duality. So here's an example. Supposing we take the functor 2 times x. So fx is 2 times x. And so the 1 is just any one-point set, which I guess traditionally I'll call it the set containing star, where star means I don't care what you put there. So f of 1 is 2 times 1, so it's going to be this set. And f squared of 1 is 2 times f of 1, so it's going to be this set. It has 4 elements. And now we consider this chain here, and you have to figure out how the morphisms work. The limit, categorically, is just a set together with functions, ln, into it that make all of the triangles commute. So if I map into here and I map into here, then going here and then here is the same thing as going here. That's all the triangles have to commute. And in this case, you might be able to guess, especially if you have seen limits in category theory, or if you, like somebody mentioned Lavier, if you look at Lavier's book, I'm sure this probably is worked out. You would take L to be 2 to the n, which means all functions from the natural numbers into 2. And the map is, so you take so this is all the sequences of F. So F is a sequence, and what you would get as your map into here, Ln, is you'd get this kind of tuple that's iterated in a certain kind of way. It would be the tuple F0, comma, the tuple F1, comma, all the way down to Fn. And if you work out what the coalgebra structure is, so you work out, you should check out that this the limit is preserved by this functor. and then you work out what this M is. It takes a sequence to the following two things. So if somebody gives me a function f, I have to give out a 0 or a 1. So I'm going to give out the first element of it, f of 0, right? That's the very first part of the sequence. And then I'm going to get out this shifted map, which takes a number n to f of n plus 1. And in fact, so this is how it works. It would be actually the streams of binary digits. So that's what the final coalgebra is for this case. And I don't think I want to go through this, but you would figure out what co-recursion is by writing down the square and seeing what co-recursion is going to have to be in this case. But this is a little bit off the topic, and so I think I will skip the discussion of co-recursion. Here's the problem. The problem this talk is about is that the method of bar, which is actually to use this theorem from 1993, usually, in many cases, it doesn't really work. For example, it doesn't work for the finite power set functor. So the finite power set functor has a final coalgebra, but it doesn't work. Barr's theorem doesn't work, and the specific reason it doesn't work, so Barr's theorem, remember, it has some hypotheses, is that in the case of Barr's theorem, the functor would not preserve the limit. So this part about it preserving the limit it turns out not to be a freebie, right? In fact, it's frequently not true. So that means you can't use the theorem. So that's what happens here. So when does it work? So the go-to method is Barr's theorem. And when does it work? Well, it works for the constant functors. It works for the identity. And it works for anything that you could get from the constants and the identity using products, coproducts, in fact, infinite products, infinite coproducts, and composition. So it works for some kind of polynomials, and that's what we're calling a Kripke polynomial. So it wasn't our definition, and I don't even think it's very relevant. I don't even think that Kripke, I don't think that it's the right name person to name this after, but somehow the name stuck, is that any functor you could build from constants, the identity, the product and the coproduct and composition, and as a basic functor, the finite power set. So that's a Kripke polynomial functor. So then the question is it true that this has a final coalgebra and anything that you could build up like this has a final coalgebra? So that's what the talk is about. Then we want to move to another category. So how about the category of metric spaces? So in the category of metric spaces, remember metric space, I would like the metric spaces today to be metric spaces that I allow infinity to be the distance. And I would like it to be, I'll tell you more about metric spaces in a few minutes, but I also want the morphisms to be non-expanding maps. So that's a fairly strict kind of map for metric spaces, but you need to pick, to make a category, you have to say what the morphisms are. And the functor I want is something that's a little bit like power set. In this case, it's going to be the closed set functor. So take any metric space to the space of its closed sets. When I give it a certain metric called the Hausdorff metric. So I'll tell you what the Hausdorff metric is. And then you have something that's a little bit like the Kripke polynomial functors. Like it's a version of power set that's tuned up to metric spaces. And then when I ask the same kind of question, do they all have final coalgebras? And would the same thing happen if I restrict it to closed non-empty sets? Does that make any difference? Then I want the Hausdorff functor, which is going to take a metric space. It's going to take the same category. It's just a different functor. And I'll tell you what the Hausdorff functor is. It basically takes a space to the space of its compact subsets with the Hausdorff metric. And Vietoris is a version of that for topological spaces. So I'll tell you how you take a topological space to its hyperspace, something like the power set operation. And then I want to know, do all of those have final coalgebras? Anything you could build up. And the case of measurable spaces, a measurable space you could do all this kind of stuff, the identity and products and coproducts and composition. And this takes a measurable space to the space of its probability measures on it, given a natural measure space structure. And this is what's behind you know, the reason for asking about this is actually in theoretical economics and game theory. At one point, Harsanyi said, well, what is a type space? And he wrote down what kind of things a type space had to be. And it turns out that a type space actually is a final coalgebra of a functor on measure spaces to the n, where n is some number of players. So it turned out to be something that economists were actually interested in, even though they didn't have the vocabulary to call it a question about final coalgebras. So, okay, so now I'm going to tell you a little bit about how all this works. So let me just remind you how limits work in sets and metric spaces and topological spaces. So if you're given a chain of sets and functions like this is like x0 and then a function from some set x1 into it and something like that. So this is just a set, a bunch of stuff like that. The limit in the category of sets is actually the set of functions that you get by picking out a point in each capital X, right? So it's the set of sequences little xn that belong to the corresponding set big N that work well with the functions. So that means that
when you say how limits work, it's just for these diagrams that are these straight
that's
chain
right.
diagrams.
Right. This is how you calculate the limit of this kind of a diagram in the category of sets.
Right.
That's it. So it's the set of sequences that follow the functions, and the limit projections, that means the maps little ln like this, actually are just basically, it takes a sequence to the ln takes a sequence to the nth term in the sequence. It's a very natural construction, and so that's the categorical limit in this case. Now, in the category of metric spaces, if all of these are all non-expanding maps, then basically it's the same set. So, but I have to tell you how the metric works on sequences, and the distance between two sequences is the supremum of the distances between the factors, like this. So that's how you get the limit in the category of metric spaces. And in the category of topological spaces, okay, so now in the category of topological spaces, now all these are topological spaces and the functions are continuous functions. The limit is again the same set of sequences, and you have to say, well, what is the topology on that? Basically, it's the topology that has as a basis the inverse images of the opens in each of the factors. So you take each space xn and you look at all of its open sets, and then you look at all the sequences whose inverse image under the map ln is the given u, and you take all of those sets and you make them the basis of the topology. So that's how you calculate limits in these kind of spaces. The reason I want to do this is because I want to use, if I could, I want to use Barr's theorem, which actually is talking about limits. So I have to know how to calculate them if I'm going to work with that. So here's the story about the finite power set. And here's the kind of why it sometimes works part of the way it doesn't work. So the power set functor preserves one-to-one functions. So that means if a function is one-to-one, then when I hit it with finite power set, it's going to be one-to-one. And in fact, something is better is true. It actually preserves all pullbacks of monomorphisms. If somebody gave me a limit like this, as in Barr's theorem, then if I could hit power set on the whole thing, and I could also take the limit of that, and there would be a canonical map here, and it's going to be a one-to-one function. So this is actually combinatorial. What I mean by that is the proof of that is going to involve the infinite versus finite pigeonhole principle. That's at the heart of the matter here. So here's how that's going to get used. So what that means is that, so in Barr's theorem, I started with the final object 1, and I iterated this like this. I'm going to now call this V0, V1, and so on, because I want to avoid the superscript here. So I'm going to call this V0, V1, and so on. What I do is I take the limit of that, L. So L is the limit of the top sequence. And then I start doing it again. So I had L is the limit here. And what I kind of pointed to is that actually going from FL to L is monic. That means it's a one-to-one function in sets. And that means if I start iterating that, the functor preserves monomorphism. So that means all of these in my second iteration are going to be, the second iteration starts here, are going to be one-to-one functions. So if all of these are one-to-one functions, it means that they're actually like smaller sets. So here's a set. This is a one-to-one function is like a subset. So this is a subset of that. This one is a subset of that one. This is a subset of that one. And that means that the limit of this second batch is actually its intersection. And the intersection is preserved by the functor. Why is that? Well, in fact, this functor preserves, like I say, preserves actually pullbacks of monomorphisms. So it's not hard to check that. And this is actually a pullback of something even, it's a pullback of monomorphisms. So it's even better than that. So the intersection is preserved by it. And then you basically look at the same proof that Adamek did, the same proof that Kleene did, and you would check out that the second infinite limit, which is going to be called V omega plus omega, is the final coalgebra. So this notation here means the final coalgebra. So let me say this again. What you do with the finite power set functor, if you start to take the limit a la bar, which is back over here, the limit is not preserved by the functor. So you can't really use his theorem. But the canonical map M that you get here is actually a one-to-one function. And that means that you could iterate this thing again. You iterated a second infinite batch. And now all these are subsets of each other, and you can take the limit of that sequence, and that is preserved by the functor, because that's like a decreasing sequence of sets, and you could easily check that the finite power set preserves that. So then the same argument shows that that limit is the final coalgebra. So we're not getting it from Barr's theorem directly, we're getting it from Barr's theorem twice. Barr's theorem applied to a second kind of infinite iteration. And in fact, this was actually done, well, it was done for the finite power set by James Worrell in a 2005 paper. So he was the one who first noticed this. And what we did was we checked out that it actually, hey, it works for all of the Kripke polynomials. But this is a little bit unsatisfactory because it's actually fairly hard to see what this second limit is. And Worrell's paper has some descriptions of the second one, which so were very insightful, and he put them down without proof, kind of like he could see what it was going to be and didn't actually write the details down, but we worked out how to actually do what Worrell did, do what Worrell saw, prove what Worrell saw. And I don't think I definitely don't have time to get into it tonight, but if anybody's interested, I could discuss it afterwards. And I want to tell you a little bit more. So here's the chart of set functors. So this is all of the, this is not all the functors that I know, but this is a large class of functors on sets. And this is the kind of things you might ask if they preserve, categorically. Do they preserve pullbacks? Do they preserve weak pullbacks, inverse images, intersections, finite intersections, monomorphisms, that's one-to-oneness. And so you could see that preserving one-to-oneness is a very weak property, almost everything you put down. So polynomial functors are, what you get from the constants by using products and coproducts and composition. Then there were the power set guys that we've been dealing with. This is the distributions. That means like an infinite version of the measure without a measure, just a countable set of points that add up to one. And a bag is a multi-set, so that's a functor. Filters on a set, that's a functor. These are sort of more pathological ones, so I don't even want to talk about them, but people came up with them just because they preserve various things and don't preserve other ones. And you could see that our result would hold even if you change the finite power set functor to, let's say, bags. If you really want to work with bags, you could do that. It wouldn't work if you changed it to filters, because filters don't preserve all the intersections. And I even think that the filter functor doesn't have a final coalgebra on sets. So some of them do and some of them don't. And so we're interested in like all the results like this. So how about metric spaces? So in metric spaces, the version of power set is what's called Hausdorff. So Hausdorff functor takes a space X to the set of all of its compact subsets, And this is the metric on compact subsets. It's called the max-min. So you take, for each point and each, so this is how you map two sets. What is the distance between sets? Well, what you do is you take the distance from a point to a set, is the infimum, like this, and then you take the max like this of anything you could possibly do. Since we're dealing with compact sets in a metric space, they're closed. So these infima are realized. And if you look at how this works, the distance from the empty set to anything is actually infinity. So that's why you need to work with the category of metric spaces that allow infinity. And of course, just like power set, just like every functor in this talk, the way it works on functions is by direct images of sets like this. And so here's some facts about this. I mean, if a set is complete, then, I mean, Hutchinson proved basically in his famous paper on fractals that H of X is also a complete set. And the finite subsets are dense. I mean, they're all finite subsets are compact, and this is a dense subset of that. And it preserves isometric embeddings, which means maps between metric spaces that preserve the distance exactly. So H of an isometric embedding is again an isometric embedding. And so I'm going to actually, you need to know something about this, or you need to prove something about this. So if you have a chain like this, so remember, a cone in category theory is going to be an object with maps into these elements of the chain that make all the triangles commute. And an isometric cone is one where the distance is exactly the supremum. The distance between points in M is the supremum of all the things that you get by applying the functions to the various factors. By
the way, I do have a question about a couple slides ago. You mentioned about, and I was trying to work it out in my head before I asked, but you mentioned how, okay, the distance between infinity and any set, the difference between the empty set and any set is infinity, right? Can you explain the reasoning a little bit about that, why it's infinity and not like 0 or something else?
Yeah, I mean, it's an infimum over the empty set.
Basically, you don't have an element X, right, in the empty set.
Right. So it's an infimum over the empty set, which I guess you'd have to say it's going to be the infinity. I think that's
okay.
why.
And I guess I don't know what the definition of what is an infima then.
Oh, would be the least upper bound.
Okay.
I think you have to be a little bit careful, but I think the least upper bound of the empty set should be infinity.
Okay, I'll check later, but I just wanted to ask about that because
it has to be
right. It's one thing if you write down carefully a definition of what is a least upper bound, put the empty set, and it comes out the logic.
Yeah, it's kind of a pathological case, but
I see. In other words, you don't really have like a least upper bound, so it's basically infinite.
Yeah, that's basically right.
Because you can always just put an extra number in there. Okay, I think I have a kind of idea about. Thanks. Okay,
yeah, this is the kind of thing that I don't want to talk about in front of people without knowing what I'm doing carefully. So I don't want to do this. So Hausdorff preserves the limits of cones that are isometric. And that means that, so after a little bit more work, you can show that the same omega plus omega stuff works. And basically, for any functor on the category of metric spaces, that's built up out of the Hausdorff functor and stuff like product and coproduct and composition will have a final coalgebra that you get in omega plus omega steps. So that's the same result. Topological spaces. So I think I should end it at 8. Am I right, Nelson? I will.
You don't have to end at 8.
A little bit after, but
a little after, right. Our attention deficit disorder didn't hit in yet, but it's fascinating.
Okay, thanks. I will. I won't go too fast, but I will breeze through a bit. I mean, so this is called Vietoris. So if somebody gives you a topological space, Vietoris, I think Vietoris was the one who defined this, is a version of power set. So that means I need a topological space that is that does what power set does. So the points of the Vietoris space are the compact subsets of the original space. And now you need a topology that's called the hid and miss topology. So for every open set, of the space. You look at all of the compact sets that touch it. So that's the hitting part. And you need all of the open sets that are subsets of it. That means they
This
missed it.
looks like semantics for modal logic.
Yes, totally. They're all kind of related stuff. Yeah. That's why the box and diamond are there. Yeah, that's exactly right. Yeah. So that's right. And so this gives you a topological space that's in general topology is usually called the hyperspace or the Vietoris space of the original space. And so, I mean, people were investigating this for, forever. I mean, Vietoris in 22 wrote a paper that showed that if X is compact, so is Vx. If X is Hausdorff, so is Vx. Somebody called Michael proved this. And the same thing with a stone. So stone space is a compact Hausdorff space with a basis of Clopin sets. Now, something that is a new fact that we proved was that if you look at the subcategory of Hausdorff spaces, so it has to be not just topological spaces. If you look at the so you checked out that, well, V of a Hausdorff space is a Hausdorff space. And so that means you think about this category, the category of Hausdorff spaces, that this functor preserves limits of chains. So that means it's better than the finite power set, which didn't preserve limits of chains. So that means this is better. So this thing has better properties. And the same thing would happen if we looked at compact Hausdorff spaces or stone spaces. And that means that if you do this kind of stuff and you look at the part on the Hausdorff spaces, you get the final coalgebra in omega steps. So in the case of sets and metric spaces, it took omega plus omega. But this topological one is better. I mean, it comes out in omega steps. And you get a bunch of other results that I think let me just show you them in a minute. So other people proved parts of this result before us. So in 2019, Hoffman, Neves, and Nora showed something about compact Hausdorff spaces. And that's a special case of our theorem. And for stone spaces, it was shown in 2004. But again, ours is better because it works for any Hausdorff space. And the fact that V itself has a final coalgebra goes back to 2005. Actually, Abramsky noticed this much earlier, probably in the 80s. He showed that V on compact Hausdorff space has a final coalgebra that's a stone space. And we don't know the answer to the following. We don't know if what we're doing works on all topological spaces. We only know it for the Hausdorff spaces. But I think this would be a very hard thing to do because very, very little, you don't have very much to work with categorically to do this. And if anybody wants a good general topology problem, here's one. And we also don't know whether every functor from compact Hausdorff spaces to itself has an initial algebra. We know that it has a final coalgebra, but we don't know it for initial algebra because various theorems that we know about don't seem to work. So here's some open questions. Then I'm going to have some general closing remarks. I'm going to do some of this really quickly. Yeah, okay. So I started out by talking about the closed set functor. In fact, it was shown by something related in the paper of 2004 by these people that the closed set functor actually has no fixed points at all. So we have a different proof of their result. So that means that this thing can't have a final coalgebra. So this is like Cantor's theorem for the closed set functor on metric spaces. So Cantor's theorem is a block, it's an obstruction to fixed points, and so it applies to this functor. It also applies to the non-empty one. I don't think I'm going to tell you. Worrell gave a representation in terms of trees for what the final coalgebra of this is. Trees and also graphs with bisimulation. I think it's kind of late. I think I will skip it. Going to the measurable case. So this is what you need to do Harsanyi type spaces. This is on measurable spaces. With a student in 2004, we showed that every polynomial functor in this, so that means every functor you could build in this kind of way has a final coalgebra. But actually, it's a totally different method. It actually uses a version of modal logic for that was known by the economists. So it was kind of inspired by work of Aviad Heifetz and Dov Samet and some other people. But this settled a bunch of questions for the economists. But as for sort of this talk, it's totally different. And in fact, you could also look at Freyd's theorem. So Freyd showed that the unit interval is the final coalgebra certain functor on a certain category. So Freyd showed that the unit interval is a final coalgebra, but his theorem isn't proved like any of the theorems that I did today. So what did I do today? Well, I gave what I'm calling the omega plus omega method, which is giving you a sufficient condition for when you get a final coalgebra iterating in omega plus omega steps. And if, just to make a shameless plug here, if you're interested in all this, so there's a book that we're finishing on initial algebras and terminal coalgebras. So terminal means final, and it's got a lot of chapters. So just general study of algebras. And this is about finite iteration. So that's kind of what I talked about today. This is about how you do it in enriched categories, like you want to solve domain equations. This is what happens if you do it in transfinite. This is the study of well-foundedness, categorified. This is a bunch of other stuff, and then a bunch of other stuff. And what I did today was section 15.2 and 3. So that's what was going on. And the whole thing also has a huge amount about like what are the properties of set functors, and that chart and stuff like that about set functors is here too. So if you're interested in that, you can look for the book. That's my.
I see. So you've shown us the final chapter, and so now we're encouraged to read the 14 chapters that lead up to it if we want to understand.
That's not that isn't really right. I should say it's not that you actually need to know 14 chapters to do it. You in fact could look at all this stuff after about 3 chapters. It just didn't fit in. So it just didn't fit in the sequence of anything else.
Well, when's the book coming out?
Whenever it's finished. So we're working on the index. So it's coming out. It's definitely we're doing the index. It's coming.
Very nice. Very nice.
Please let us know when it's ready. And
okay, thanks. Somebody's chatting me.
Is there a draft version available?
I think if you wrote to me, I'd have to find out. I'm not even sure that we're supposed to do this anymore, but there might or might not be. Thanks, Janis.
Anyways, thank you for a great speech.
Well, I'm sure that I might quickly, but people feel free to ask questions, everybody. Thanks.
Please. Any questions?
I have a broad one on which I'm not sure how this work relates at all. It might not, but right, there's one place that all this coalgebra stuff is studied is in domain theory, right? And you've got a couple of interesting things there, which is you have categories which you really have like a ton or all coalgebras almost, or whatever, all terminal coalgebras, I should say, final ones. And you've got the setting for co-recursion, and then also in domain theory in particular, as opposed to, you've got this property of certain categories where the initial and final initial algebras and final coalgebras coincide, which is very unique and special. And then I'm wondering if in any of the settings you've carved out and are looking at that are the sort of more interesting ones, that you've got any properties like that, or how any of the topological settings you're looking at might be similar to any of the topological settings used in domain theoretic models.
Yeah, okay, right. So in fact, we have I think we have the best treatment of this. So we looked at all the treatments of it, and we have this is what you mentioned is the limit co-limit coincidence. So that means sometimes the initial algebra is a final coalgebra, that backward. So it's basically it. And so what we know what you need is you need to work in a category that's enriched over CPO. So that means that the morphism, the HOMs are not just HOM sets, they're HOM CPOs, and that the composition operation has the right properties like that. And then so basically we've taken all these kind of lemmas from Plotkin and Plotkin's paper and Smith and Plotkin's paper and actually improve them by lowering the number of assumptions you make in this, and this is that theorem. And the one about metric spaces, well, so this is what you do in domain theory. And for the metric spaces, it's similar. You need your category to be enriched in complete metric spaces. And where is that going to be? It's going to be the next section here. Enriched in metric spaces. And again, you need to know something about how the Hom sets work. The Homs have to be non-expanding functors. So that means the distance, you need various contractions, actually. You need the things to be Hom contracting or various kind of stuff like that. But after you do this for a while, you again get a limit coincidence. So in fact, in all the cases that we're aware of, they come out of 2 or 3 results. And I think by now we understand it fairly well.
That's
So
beautiful. Thank
if you want to read,
I look forward to reading more about that. Yeah.
okay, thanks.
Yeah, again, let us know when the book is ready.
Okay, sure. Thanks for your enthusiasm and interest. Yeah.
Great. Any other questions? Anyways, let's thank the speaker again. Larry, it's always a pleasure. It's always a pleasure.
It's a pleasure to be here, and I'm sorry that I haven't been faithful at the New York
No.
Category Center, but
No, it's
wonderful.
okay. It's okay. Anyways, Larry, whenever you want more, we love your stuff. I don't know, it's great stuff. Anyways, ladies and gentlemen, we're not going to meet next week, but in 2 weeks we meet again. I don't know what the title. There's no title given yet, but something Sato Pedro or something is speaking. Anyways, have a wonderful evening. Thank you very much, and stay in touch, please. Take care.
Take care.